Welcome to this video. In this video, we will be discussing Hamming codes. If you have seen my previous videos, you probably have heard about Hamming distances. Now, Hamming codes are different from Hamming distances. So we have studied about parities, CRCs, checksums, and many different ways of detecting bit errors during transmission. But we have not studied ways to correct bit errors during transmission. So detection is one thing, correction needs even more information in the code word to be able to not only detect an error but also to correct and pinpoint the location where the error has happened and correct that bit error, right? To be able to do that, one of the ways is to use Hamming codes. And as I said, unlike parity, where for example, if you have a 5-bit data word, you just add 1 bit, right? To either make it odd parity or even parity, and then you'll be able to detect some kinds of bit errors like odd number of errors and things like that. But to be able to detect and fix the error, right, you need even more data to be added to the data word while making a code word. And for Hamming codes, you are able to correct a single bit of error. So while transmitting the code word, if a single bit of error has occurred anywhere in the code word, you will not only be able to detect that error, but you will also be able to correct that error, only 1 bit though. So if your data word has m bits, okay, and so you use this formula to figure out how many extra bits you want to add to the data word to make your Hamming coded code word. Okay. And R is the number of redundant or extra bits that we are supposed to add to those M number of data bits to be able to create a Hamming code. So for example, if you have 7 bits of data, so M equals to 7. So here R should be 4 because 2 to the power 4 is greater than equal to 7 plus 4 plus 1, which here is equal to 12. So 3 would not have done it because 2 to the power 3, which is 8, is not greater than equal to 7 plus 3 plus 1, which is 11, right? But 4 will do it. Okay, so we need at least 4 bits of redundant data added to the m bits of, 7 bits of data here to be able to generate a Hamming code. Okay. So where do we add those redundant bits? Like CRC, we do not add those redundant bits to the end of the data word. Here the redundant bits are dispersed, they are spread throughout the body of the code word. For example, if you take 7 bits, and as we saw in the previous slide that we need 4 redundant bits, right, to be able to detect a single bit error, right? So those 4 extra bits will be placed at these locations, and these are all power of 2 locations. So you took 7 data bits and we took 4 redundant extra bits. So when you combine all of them, we are going to get 11 bits as the length of the code word. Now out of those 11 bits, the extra bits are going to go to position number 1, which is power of 2, right? 2 to the power 0 is 1. Then 2 to the power 1 is 2. So we have the second extra bit going there. 2 to the power 2 is 4. So the third bit, the extra bit is going to position number 4. And 2 to the power 3 is 8. So the fourth redundant bit is going to go to position number 8. This is how you're going to distribute those redundant bits inside your code word. Okay. So let's just say you have your data word as 101, 1001, right? So 101, 101, 1001. So you start with m equal to 7 and this is your data word. you place the bits of the data word in such a way that you leave space for those redundant bits, which are going to take the positions which are powers of 2, right? So this is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, and this is 2 to the power 3. You start the positioning not from 0 but from 1, okay? And then you put the data word bits in this way, like 1 0 1 1 0 0 1, and just leave R1, R2, R4 and R8, right? These are the redundant bits which we are going to figure out how to find the values of those bits so that we can put those values and send this combined thing as the Hamming code, right? Okay, to be able to figure R1, you only consider bit positions where the first bit, the rightmost bit, is a 1. So at position 1, if you write this position in binary, you get 0 0 0 1. If you write 3 in binary, you get 0 0 1 1. But if you write 2 in binary, it is going to be 0 0 1 0. The last bit is not 1. So in all of these cases, the last bit is 1. So to calculate R1, we need to consider these bits. This one. These bits have to be considered, okay? Basically every alternating bit, right? And how do you calculate R1 here? We do even parity. So let's calculate how many ones are there when you consider all of these positions. So here we have a 1. Here there is another 1. Here there is another 1. Here there is a 0. But here there is a 1. So there are 4 ones. So we need not add any more ones to make this even parity. So R1 is going to be a 0. So R1 has been calculated. To calculate R2, look at this place here. We have already added the 0 there for R1. This is supposed to be R1, right? Okay. So to calculate R2, you look at only those bit positions where the second bit is 1. Okay. Look at all of these positions. If you write those position numbers in binary, you figure out that the second bit from right is 1. Right? So they are like in groups of 2, every other group, right? So here you have 2 and 3, 5 and 4 are not there, then 6 and 7, 9 and 8 are not there, then 10, 11. It goes that way. Okay. And we figure out R2. So let's count the number of ones. Here we have a 1, here we have a 1, this is a 0, here we have another 1. So there are 3 ones. To make this even number of ones, we need to make R2 as 1. Okay. All right. So now that we have our R1 and R2, let's try to figure out R4. Now for R4, you write the binary representation of all the positions and look at only those positions where the third bit is 1. Okay, third bit is 1. So this is just a group of 4 numbers here. Because we have only 11 positions, you can only find these 4. Had this been longer, then even more positions should have been there, right? Okay, so let's calculate R4. So what numbers do we have in these positions? So we have 1 1. That's it. That's the only one, and that is present at position number 7. So we need to make R4 as 1 to be able to make the number of ones even. Okay, so now R4 is also 1. Here we have R1, here we have R2, here we have R4. Let's calculate R8. To calculate R8, you need to only consider the bit positions where the fourth bit is 1. Okay, fourth bit is 1 for all of these bits, and number of ones is 1, 2. So already 2 ones are there, even number of ones are already there. So R8 needs to be a 0. Okay, so basically this is what we send as the code word, the Hamming code, right? And this is R1, this is R2, this is R4, and this is R8. Okay. Now let's just say some bit got changed. Now let's just say this 6th bit here got changed from a 0 to a 1 while transmission. So how do we not only detect that there is a problem, so how do we pinpoint where the problem was so that we can go and fix it? So what we do is we try to find the parity again by doing the XOR operation, right? To see, if we have even number of ones or not. So for R1, what do? We look at these positions, right? As I told you before, we look at the positions where the last bit, the rightmost bit is a 1. So how many ones are there here? 1, 2, 3, 4. 4 ones are there. So we do not have to add any more 1 to make it even. So we write a 0 here, okay? All right. To be able to calculate R2, which is for this guy, right? So which numbers do we need to consider? Which positions? Like this, and this. These positions have the second bit as 1, as I told you before. How many ones are there? 1, 2, 3, 4, 5. There are 5 ones. So the parity is going to be 1 if you want to keep even parity. Now let's consider R4. 1, 2, 3, 4. This position, right? For this position, we need to consider only these 4 bits for the R4 part. And how many ones do we have? We have 1, 2, and 3. So 3 ones are there. To make it even, we have to have a 1. Okay. Now for R8, 3, 4, 5, 6, 7, 8, which is this position here. Okay. We need to consider these ones also. Okay. Now for R4, the third bit has to be 1 for all the positions. For R8, the fourth bit has to be 1 for all of those positions. And we have 1, 1, 2 ones. So we already have even number of ones. So the parity is going to be 0. As you can see, any bit, any of those R's, those extra bits that involve the place where there is a problem, right? Their parity got modified. In this case, only in this 2 cases, the parity got modified because they involve the 6th bit. For this guy, it does not involve the 6th bit. For this guy also, it does not involve the 6th bit. That's why the parity checks out. Okay. If the 6th bit had not gotten altered, then even these parities would come out to be 0. So if you get a 0, 0, 0, 0 for basically R1, R2, R4 and R8, there is no problem. There is no error. But here we have 2 ones. So basically we get a 0, 1, 1, 0. And 0, 1, 1, 0 is 6. So this tells us that there is a problem at the 6th bit. And so we go and change this bit to a 0. Now if you recalculate all of these different parities, you are going to get a 0, 0, 0, 0, thus indicating that there is no problem. Thank you.